I want to get a couple of housekeeping things out of the way before, but first of all, thank you for joining for today's session. I'm one of the co-hosts today. My name is Hirsch. I'm a partner solutions engineer here at Cockroach Labs. And alongside with me, we have Art from who's also partner solutions architect at AWS. But before we get started, we have a few reminders for you all to get the most out of today's session. So if you have any questions, please use the Q&A function to submit those questions. We'll be taking time at the end of the session to review the Q&A, but we also have a couple of folks from the Cockroach Lab side who are reviewing in the background, and if they can answer while the session's ongoing, they'll do their best to help out and answer those questions. And after the session ends today, the team will be sending out a link to watch the session on demand over the next couple of days as well. So, having said that, again, I'm just going to introduce myself a little bit again for some of the new folks that just joined in. My name is Hirsch. I'm a senior staff partner solutions engineer at Cockroach Labs. Alongside with me, I have Art Siddiqui, who's, you know, or I should say Dr. Art Siddiqui, who's a senior partner solutions architect at AWS. Art, you want to go introduce yourself?
Yeah, thanks, Josh, for having me here. Hi, folks. Art Siddiqui from AWS. I've worked with the Gen AI team dealing with partners such as CockroachDB, and I'm looking forward to this session with you guys. Thank you.
Awesome. Thanks, Hart. So for today's agenda, we have a couple of opening remarks that we just kind of went over right now, but we also want to get into what AWS is doing, and especially in the AI space. And then for folks who are not too familiar with CockroachDB, we're going to do a really quick overview, a crash course on what CockroachDB is, and then dive deeper into how you can use CockroachDB as a vector store and how you can use CockroachDB and AWS for, yeah, fraud detection use cases. So that's our overall agenda for today. It's going to be a lot of content. I hope if you have any questions, don't be shy. Feel free to put them in chat. But having said that, I'm going to pass this off to Art.
Thank you, Hirsch. Appreciate it. As I said, hi, folks. I'm Art Siddiqui with AWS partner team. And as the AI agents have, for the most part, taken over the world by storm. At AWS, we believe that there soon will be millions of agents in the world where they're working alongside the humans. And one of the things that I like to mention here is that these agents, unlike foundation models, they're able to do tasks, they're able to take on actions, they're able to accomplish goals. And this is unlike what we know of foundation models today, where for the most part it's a request response. But with agents, we're able to see where they can potentially take on actions in the physical world as opposed to simply sending us a response. So if you're looking at this from agents in terms of evolution of AI agency from low to high, if you recall, we started with rule-based software systems, simple automation, and we kind of moved towards AI assistants, chatbots, and again they're used today. The real transformation is going to be where we can provide a goal or give a goal to these agents, and they are able to operate independently for the most part and achieve these high-level objectives. So if you're looking at this where it can potentially apply, at AWS, we see there are 4 key areas where agents are able to provide tangible values, and that's the key here for us to be able to see a return on investment, a tangible value where there is benefit that's realized in different use cases. So the easiest one to kind of talk about is workplace productivity, which the most accessible entry point for any organization, we believe. The focus is automating core workflows. This could be across many departments, as we've seen, sales, marketing, HR, finance. We're seeing quite a lot of movement in the customer support space. And this is where the Amazon Quick Suite comes in. It can eliminate chaos by creating an intelligent workplace where teams and AI agents can work together, which is the sweet spot, right? We don't foresee agents replacing, uh, I guess, humans if you go that far, but we're seeing it as a way for these agents to augment what we do and provide a level of productivity. And the next one, and this has been around for some time, is how AI is transforming software development in the workplace. With Gen AI and agentic AI, we're seeing a fundamental evolution in how software gets built. Just think about it, in the past few years, we moved from traditional programming to code completion to chat-based programming, and now we're seeing the concept of vibe coding, where developers and AI are collaborating in real time. So how far is this going to go? Think of it where we have agent fleets, right? Systems that can plan, build, and test and deploy software autonomously, and that's where we're heading. Where is the next area? For customers with differentiated needs, the priority is to quickly and easily build custom agents that can potentially span models, frameworks, and even different cloud providers, right? And this is, if you want to understand this level of complexity, we need to pause and take a look at the anatomy of an AI agent. Agents have memory for context. They use tools to take actions in your system, potentially on your behalf, or because they need to achieve a goal as part of their direction. They have LLMs as part of their intelligence layer to um, provide them guidance potentially. Data for domain knowledge. We see observation and guardrails that provide them a level of responsibility and ethical behavior. Actions are essentially what we want agents to do. This is what they need to perform, and they need to continuously do that until they achieve a goal. But as I said, user interaction is important. We won't get into a place where agents are completely autonomous. There's going to be user interaction potentially at every step until we feel comfortable with these agents being more and more autonomous. Last but not least, um, you know, is the organizations that are not looking at agentic AI as a one-off deployment, but looking at it as an evolving operating model of how they achieve growth in their business. They're building what can be thought of as an agentic OS, a secure governed platform that potentially supports a fleet of AI agents. Now, this could be for employees, this could be for customers, this could be a way of you bringing your employees closer to customers for potentially more close interactions. Now, this is where, as I said, this is where we're seeing the industry evolving. And to that end, if you're looking at as what we just discussed, AWS provides models, frameworks, tools, and for the most part, AI infrastructure that spans silicon, data foundations that help organizations ensure their agentic AI evolution is going to happen smoothly. Now, we've been doing this for decades. We've been building secure, resilient, global infrastructure for decades, but now we're using that infrastructure to build an agentic AI platform. To that end, I will pass the torch back on to Harsh to talk to you about CockroachDB. Thank you, Harsh.
Perfect. Thanks, Art. And Art mentioned a couple of things around agentic AI, and especially some of the tools on the AWS side, like SageMaker and Bedrock that you briefly saw in the architecture diagram earlier on. So we'll cover how you can, how those are going to be leveraged for, the fraud detection later on. But just wanted to preface it with that as well. But right now, what I want to do is Give you an overview of CockroachDB, especially with a lot of people here. There might be new faces who aren't that familiar with CockroachDB. So, what is CockroachDB and why we're kind of named? We have that name, right? So, before I dive deeper into CockroachDB, I just want to kind of preface it with like start off at we all know that application requirements have changed, right? So, if you take a look at this in terms of scalability, a lot of you if you're based out of the US, probably know about the GameStop squeeze that happened in 2021. That at the time it was record-breaking volume of transactions occurring in the trading space at 955 million on a single day, on a single trading day. Then we had April 4th, April 7th, and April 9th and basically you'll see that week or so where you had record-breaking transaction volumes again. Those were the days when our president, who were here in the US, announced tariffs. And if you can remember how much volatility that brought in the trading markets. And we saw transaction volumes ballooning, breaking their own records over and over again in the span of days. So what that tells us is, these are not one-off events. Your systems need to be able to scale immediately when required, right? And then the other part is they need to be resilient and reliable. Art might not like me saying this, but it's a story that we both share. I was at an event at the AWS office in October when that outage happened, and I was scrambling to put my demo together because I put it up on US East 1, where the outage actually occurred. And that kind of reinforced my compassion for all the developers and everyone that have to go through, all these planning and everything for to survive these sort of events. But at the same time, what I also said during the session I had over there was this is not going to be a one-off event. It was AWS today, it was Google a few months ago, and and as I predicted, we had an Azure outage, I think a week or so after that. So your systems need to be designed and architected to be resilient and reliable. These are modern requirements now, and they need to serve a global user base. Your users are potentially all over the world. Your database needs to scale, your application needs to scale across multiple regions, across across a cloud and a hybrid way and be able to partition data as well, geo-partition, tag data to specific locations and comply with these complex regulations and where your business is operating. And alongside that, developers today are not just dealing with, SQL data or SQL tables and a SQL database. They're also dealing with, NoSQL, unstructured data, JSON documents, spatial data, and now with AI being everywhere, they're going to be dealing with vector data. Um, if they're not already dealing with it, they're going to be dealing with it very soon. So your database needs to be flexible as well. But it needs to be more than just those. And these are some of the other requirements. I'm not going to go through them all, but basically, it can't go down, be resilient, zero RPO, minimal RTO. It can deploy anywhere and really helps you comply with all these regulations, right? So that's where those are the challenges that really built out the ethos of what CockroachDB is. So it's a relational database. It's a distributed SQL database that combines the best of a relational database with the best of a NoSQL database. So if you want to think about it, we those two databases met and they merged and they took the best of what they had to offer and we put it into one. So with CockroachDB, you still get the strong consistency that you're familiar with, ACID transactions with relational databases. You still can like actually do transactions. You can have stored procedures, triggers, etc. And it's Postgres wire compatible. But alongside it, it can scale like a NoSQL database. It can scale horizontally, it can scale vertically. You can do online schema changes without the database having to go down. You can do rolling upgrades without downtime. And at the same time, what we ensured from the architectural perspective was we designed it from the ground up to be cloud native. We did not take Postgres and fork it and make it distributed. It's not a Frankenstein in that sense. Um, it was architected from the ground up to be distributed. So that's what sets CockroachDB apart. We gave it, we made it compatible with the Postgres wire protocol on top. So to you as a user, when you're interacting with CockroachDB, it looks and feels like Postgres. You don't have to learn a new language. But at the same time, from the operational perspective, you get 5 nines of resiliency, you get a truly cloud native distributed architecture, you get elastic scalability. And you can run it on anywhere you need to. You can run it on AWS Outposts, you can run it on EKS, you can run it on multiple regions, hybrid, name it. And all while, making it enterprise ready, supporting like giving you PCI compliance, HIPAA compliance, GDPR, giving you the capabilities of data locality, data domiciling, deploying in, hybrid fashion, and also supporting different, Kubernetes distributions on AWS as well. So now let me get a little deeper on the overview, right? So unlike traditional relational databases, CockroachDB is built to be distributed. It's not just a single instance, it's distributed across multiple instances. So instead of, like I said, a single instance, the CockroachDB cluster is a single logical database consisting of multiple nodes that that make up that distributed system, right? And because the CockroachDB database can scale out into multiple nodes, you can just add, volume and capacity of the data that you're storing, as well as, amount of transactions that you need to process by just scaling the cluster horizontally by adding the nodes to the database cluster, all while being a single logical database. But because of that, you can scale it across multiple regions the same way as well, while it's still being that single logical database. So forget the days of when you need to like, set up those complex, downstream or CDC pipelines or, that you would with other databases where you're deploying, databases in traditional databases into different regions and making sure that, the data is replicated properly across that. CockroachDB handles all those tasks natively. And not just multiple regions, like I said earlier, you can deploy it on AWS in multiple regions. If they don't have a region somewhere, you can use Outposts or you can use your own data center and have a hybrid deployment. So that's the flexibility and scalability that we provide. But what that enables us to really do is also with that multi-region capability, do location-based data pinning. So let's say you have you know, a com you have to a regulation that you need to comply with, like GDPR or CCPA, PA, California Consumer Privacy Act, right? It's a handful. But essentially, it's a regulation that if you don't comply with, your organization is gonna face fines. What we enable you to do with this, with the database is, hey, we already scale it across multiple regions. Now you can, as a single logical database, now you can pin data that needs to be in a specific region to a specific region without added operational overhead. So it makes complying with those regulations very simple compared to whatever, is out there right now from the legacy perspective, right? But on top of that, as I said a little bit earlier, developers need flexibility. So we support, we store everything within CockroachDB as tables. It's a relational database that's distributed, right? So you already have, you can already process SQL transactions, but we also have JSON support as well. So you can store JSON documents within, through JSON-B support. We have spatial data support, and now we also introduced vector data support as well. So you can store vector embeddings right on your OLTP transactional database. And with the architecture I mentioned earlier being distributed, right? What we do is we do consensus-based transactions to make sure everything, follows ACID compliance and serializable isolation by default to make sure everything, all the transactions and, consistency is guaranteed. But the benefit of that also of, using consensus underneath with your architecture is that gives you the ability to survive failures. So as long as you maintain a consensus or a majority, you have the ability to survive, node downtime or a couple of node downtimes or even like beyond that region downtime. So for example, a lot of our customers last month, even though East One was a region where they deployed our database on for their use cases, they're spread across multiple regions. So they were able to, still just point their existing local application to another to the exist like it automatically to a load balancer in another region and automatically took care of everything while that region recovered in its own time. So based on whatever your survivability goals are, you can survive them with CockroachDB, and that's kind of where the name comes from as well. So it's a distributed database. It replicates. You can scale it really fast, and it's really hard to kill, just like a cockroach, right? You can get rid of one, but you can't get rid of them all, and that's kind of the story behind the name. So having said that, that's kind of the CockroachDB overview, a crash course, if you may, into what we do. It's high level, but I really want to get into what we're doing in the AI space, especially as a vector data store. I want to dive deeper into that, and that's what I'm going to do next. So generally, databases. I title this databases in the AI era, but really the way that I see, the computing eras are um, there was a PC computing era in the 80s and 90s then, and even a little bit of the 2000s. Then with 2010s, blend in 2010s and 2020s, it turned into the mobile computing era. And now with, the LLMs that you see, AI agents that Art was referring to, we're diving deep into the AI integrated computing era. That's how I personally just define those eras, right? And within those eras, the purpose of a database has largely remained the same, but how they've operated has kind of changed. So within the PC computing era, you had your traditional relational databases. Within your mobile computing eras, it was a blend of NoSQL databases because you had a lot more unstructured data that you were dealing with. And you now, with the volume of data that was increasing and with, modern requirements, as I, kind of shared earlier, that's where, distributed SQL databases came into existence with those requirements. But as we move into the AI integrated era, you still need the benefits of a distributed SQL database, but you also need a vector DB to store all those vector embeddings that are going to be used by LLMs and AI agents and whatnot. The way that and this is a very simplistic way to think about vector embeddings or vectors in general, but the way that I think about vectors is they are to your AI models as what kind of binary is to computing. It's not a one-to-one reference, I would say, but it's just a good way. Like that's that's what these AI models are going to leverage to make those contextual decisions. So you need a data store to be able to store those. So and with Gen AI, with Chat GPT, right? User behavior is changing a lot. So I think in 2021, a little bit of 2022 as well, up until Chat GPT came about, I think majority of us used to go on our favorite search engine and type in what we needed. We would be given a list of search results, and then we'd go through them to get the information that we need. Now with AI, that has kind of pivoted to it being a answer engine. Like we go into the chat interface that whichever AI model that we're using, right? We give it the question that we need answered and provide some context around it. And we don't want search results anymore, simply put. Like we want an answer. It's great that we get contextual, like, citations of where they're, getting those details from. But our behavior fundamentally as users has really changed. So, so you have to take that into account. But because of that, requirements from the application side have changed as well, right? Now, if users are so used to, using answer engines or, LLMs for everything, if you're building applications, they probably want something similar. And this is where you're building your RAG type architecture, search and retrieval, right? Your retrieval augmented generation architectures to give them contextual responses based on their query from the data that we have for the query that they're asking, right? So this is where, a vector database becomes very important to implement those sort of architectures. And there are some hurdles that we have to get over for, Gen AI adoption. Like, a lot of you here today probably saw, 95% of enterprises have, tried a Gen AI pilot, and um, I mean, only 95% of those pilots actually failed. Only 5% actually went into production and they moved forward with. They're having issues with, data quality, data readiness, legacy infrastructure and systems are not really meant to serve those AI use cases. And building AI applications at scale is really hard because of the amount of volume of the data that you're dealing with. And I'll show how hard that really is in a couple of slides. And these are just some of the challenges that, you see overall from users and, organizations as they're trying to adopt AI. And another part of that from the database perspective is legacy databases, a lot of them don't support vector. If they do, they can't scale as easily. And if they don't support vector, you're as an organization, you want to enable AI use cases, you need to have a vector database and you have to migrate all that data, convert that into embeddings, and then migrate all that to a vector database. And and not all vector databases can just scale as easily as well. You still struggle with scale with the amount of volume that you're dealing with. The reason why is because let's say you have this, these three phrases over here: a boy is walking, a girl is walking, I'm studying, right? And you create an embedding out of it. When it's just that phrase, when you're storing that in a database, it's like 14 bytes roughly. And now when you make it go through an embedding model, you create a vector embedding out of it. The storage per that vector dimension bloats bloats up to 3 to 4 kilobytes. So that's a 20,000 to 120,000% increase. So just the amount of volume of data that you already had on your database, just because you converted into a vector embedding, it's going to lead to a lot of bloat in the volume. So that's where we kind of took a crack at, okay, we need to really address this problem as a vector store as well. We're already a distributed SQL database. We solve the challenges of scale, resiliency, and, pinning data and being always on, right? But let's solve this challenge as well. So we introduced vector search in CockroachDB 25.2 as GA. So now you can store vector embeddings alongside your OLTP data right within CockroachDB. In addition to that, we also give you options and functionality to do similarity searches within CockroachDB, like L2 distance search, cosine similarity search, as well to enable those AI use cases that you may have as an organization. So fundamentally, what it kind of looks like is you have your OLTP data on database. You're already storing that as a table. You can also store JSON-B data as well. But now you can also store vector embeddings as another column right within your table. So that's great. But now the challenge is with all that bloat and all amount of data I have, how do I quickly search through everything? So that's the next part of the problem, right? So that's where we introduced recently a distributed vector index called C-span. So as an organization, as from the engineering perspective, we looked at a lot of options from the perspective of what are the best vector indexing algorithms out there right now. So there's a couple from Microsoft, Span, SPFresh, and Google has Scan. And then you also have to deal with bloat as well with I talked about earlier, where you have um, you know, 14 bytes, the example I gave, turning into 3 to 4 kilobytes. That's like from anywhere from 20,000 to 120,000% in data bloat in terms of volume. So you have to look at quantization techniques to reduce that as well. So we implemented a rabbit queue quantization as well. And the reason this is unique to CockroachDB is this isn't just a, a vector index, it's a distributed vector index. So so it's really optimized for a distributed SQL database. So all the benefits that you're already getting with storing OLTP transactional data with CockroachDB, you also get the performance benefits with this index of storing vector embeddings with CockroachDB as well. So vector index, it's in preview. It's I'm not gonna say when it's gonna go GA, but soon. But what that allows you to do is it allows you to scale without bloat. Speed up, searches because the data is indexed, and and you can store these indexes by user by region as well. So like if you're doing very specific searches, you have that granularity with defining those indexes to give you the best sort of performance that you need for your use cases. So that is what we're doing from the vector store perspective. We didn't, take it for granted from the perspective of, oh, we just want to implement a new vector store. We want to actually build something that makes sense and is usable by organizations to address the challenges that we see. And having said that, this is what I'm really excited about next. Fraud detection with CockroachDB and AWS. So I know it's been a lot of slides so far, but this is kind of what I know a lot of people here are, signed up for. So let's get to it. Um, so let's just start with the business stakes, right? Fraud controls aren't just a cost center. They protect conversion, they protect customer trust, and they protect the brand. When approvals and decline decisions slow down, a lot of these carts get abandoned. Don't ask me, just maybe ask AWS when Black Friday comes and if there's a lot of fraudulent alerts where these decisions don't go down, people probably don't buy that quickly, right? Carts get abandoned when they fail. And and these approval and decline decisions are important. They block they block bad actors getting through and making any bad decisions, but they'll at the same time they can't just be optimized to block good customers as well. So there needs to be a balance in which and how quickly you alert, like get those fraud, like detect fraud, and it's alerted, and that process needs to be optimized. And the thing is, I talked about the recent outages that happened with all the cloud vendors, right? And these things, the way that I think of it, they're not just IT hiccups. These are going to be business events that you have, as an organization, have to architect for regardless. You can't just rely on the cloud to be up. It's built by humans. There's going to be human error, and you have to architect to um, survive those events. And the goal of these fraud systems is to be always up, even when those events occur, and keep accurate approvals flowing, even when outages occurred. Like it can't like handicap your application. And today we're gonna cover like how CockroachDB is really designed for resilience. We already covered that resilience, scale, and accuracy, but we're going to see how it fits into this fraud detection model and making and optimizing it a step further. So fraud, as you know, it's a moving target. Like attackers, they adapt fast. So if we just have a rule-based system, it's going to fall behind really quickly. Their attackers are ever evolving. And on the business side, we don't want to degrade customer experience at the same time. We want to avoid fraud, but at the same time, customer experience is important as well. And technically, what that means is these decisions have to land in tens of milliseconds to make sure there's a good customer experience, while those decisions still have to be accurate as well, and still respect data privacy and everything else. So the result is there's a classic tension versus, speed and rigor and versus and friction and safety, right? There's friction with how safety we want to make it versus how quickly we need to process this. And that comes down to a business decision. So from our perspective, our approach with that I'm going to highlight in a moment is meant to resolve that tension by making resilience and correctness the default, and also using layered detection to stay adaptive to new attacks as well. So the modern detection approach is a layered approach. It's layered to improve accuracy without really hurting the user experience. First of all, if you look at the diagram at the bottom, layer one, it's a rules filter. So it's a rules layer that filters obviously bad traffic. Like think about like rate limits, impossible travel, like destinations and things that are trying to be booked, device anomalies, etc. Right? The second layer or the middle layer over here that you see on your screen is an anomaly layer. Basically, it scores weirdness in real time. So you can use machine learning algorithms such as random cut forest to catch novel behavior, anomalous behavior, right? And the third predictive layer is more of a classification layer. Uses classification machine learning models, right? It classifies risk with historical patterns. A common choice used by a ton of enterprises is XGBoost. And these layers are meant to work together to not just reduce overall like noise, but also sift through anomalies, detect new patterns, and at the same time, make fine-grained calls in detecting, these attacks, right? Right. But at the same time, latency is an issue. Like, how quickly can we get through this? Making sure that we comply with SLAs. So latency is always going to be a problem that you have to navigate. And speed, it's non-negotiable, right? You can't just have it wait for minutes at a time while you take a decision whether something's fraudulent or not. It has to be quick. It has to be part of that flow that a customer goes through. So because of that, what we can do is introduce vector similarity search as well. So basically, what that does is based on historical contextual data that we already have, stored as embeddings, you can do similarity searches that with new transactions coming in is, does this look like known fraud? And immediately like it can sift through using LLMs and all these AI models that you have now to detect these issues without avoiding brute force scans through the database. And the reason why we also have that vector index that I talked about earlier, so it keeps those similarity checks really quick inside that flow that a user is already going through with the transactions because it's being processed by that OLTP database as well. So from 1,000-foot perspective, right? What you can do is you can land all the historical data into S3, and you can train it for your machine learning models I talked about, like random cut forest and XGBoost for your anomalous and classificate predictive modeling through that in SageMaker, and stream those online events that you're coming in through Kinesis, and then have a Lambda function, do that in real time. We're also using Bedrock to generate embeddings from that historical context and store that into your OLTP record. and then use vector search, similarity search, as well as other LLMs to do quick, real-time similarity searches as an added layer to give you more accuracy and quick responses to whatever you already have to, detect all those, any if fraud is actually happening within that transaction or not. And the reason, why, CockroachDB is ideally suited for this type of architecture is, first of all, it's a single logical database that can span multiple regions. We can get correctness across regions with local read latency. So that's really important when you want to make fast decisions. And on top of that, you have vector indexing that's built in that really reduces or flattens how quickly, those searches are parsed through within the database, right? So similarity searches or lookalike searches are really fast on CockroachDB when you want to add that additional layer on top of that. And the third part is the operational simplicity. Like if your schema changes for some reason, you need to incorporate for something new. CockroachDB does it without downtime. If you need to upgrade your database, does it without downtime. If you actually had downtime on your cloud region, still survives that. And it's really easy to scale to address the volume of data that you need to store for all this to happen, right? So so that's why, like, I kind of want to think about it's beyond just a database. It's a fundamental layer in this architecture. And I talked about C-span earlier, which is our vector index. So C-span basically is exclusive to CockroachDB. It gives us a predictable millisecond level similarity search, even at very large scale. We talked about the scale. So with that, those approved decline uh, decisions are kept within SLAs that you probably set out as an organization. And the reason why is basically basically stores everything into a k-means hierarchical tree. That's how it's indexed, and it makes it really shallow and quick to sift through when you're doing those searches that you need when you have those similarity searches, right? And on top of that, what CockroachDB also does is rabbit queue quantization. So what that does is it really massively shrinks the vector embedding size by almost like roughly on average 90%. So it goes from 3 to 4 kilobytes to about 200 bytes. So that really solves a lot of issues with, the amount of volume and bloat that you have to store as in your database with the vector embeddings that you're trying to store. And with our integrations with Bedrock to, create and, store embeddings and creating a RAG architecture, as well as, integrating with SageMaker, where you can, apply those machine learning model, CockroachDB just becomes a natural fit to also store your OLTP records and vectors together. So you don't have to worry about operational complexity of maintaining multiple data silos, and everything can be done with just one database. So kind of to top it all off, right? Like what improves with this approach? The speed and scale of how everything's done. We covered that. The simplicity I talked about earlier, OLTP, vectors, JSON, spatial data, all in one database. You have global correctness. We are a strongly consistent OLTP transactional database. We follow the ACID guarantees. We implement serializable isolation by default, and we can span multiple regions and still provide those guarantees as well. So that's really important. Like your AI models, your machine learning models are only as good as the data that you feed them. And for that, your data needs to be correct. And that's where CockroachDB really excels in correctness of your data. And we're a natural fit with AWS as well. We're cloud native. We can scale across multiple regions, but we also integrate with tons of their services like Bedrock, SageMaker, Lambda, Kinesis, Streams as well, and S3 as well. So some of the key takeaways, right, for us today. I talked about this. Resilience, it's table stakes. You're going to have outages and on the cloud. You at that point you can't just blame the cloud provider and be like, okay, the cloud's down. What can I do? You have to really architect around those outages. From the fraud perspective, it's not just a cost center, it's a revenue function. It it decides what your customer's experience is going to be when they're using your application. And scale isn't just about size, it's about operational readiness as well. Um, you can scale vertically, however, or horizontally through other databases, and you can do all that complex tooling to make them horizontally scalable and make them distributed. But from the operational side, they still need to be easy to maintain. We do all this natively. You don't have to worry about it from that perspective. And from the perspective of, the decision-making backbone, CockroachDB is already integrated with these services. It's just a natural fit because of all the type of data that you can store and use to make those models more accurate and everything. And then there's on top of that, we talked about the layer detection, the three layers, but on top of that, with vector search a possibility now, introducing similarity searches for those ever evolving, attacks, as well. So that's really all we had today. I hope you got something to take out of this. But if you scan this QR code now, it should redirect you to a link where you can download all these resources, and we'll be following up with a lot of the like a recording of this session as well that you can check out on demand, but also with a couple of other things around technical blogs and whatnot that you can use to implement this yourself. So having said that, I want to say thank you from my side as well as Art's, but I want to open it up to any questions and whatnot. All right. So I have one question over here in chat. Can you explain how failover works if a region or AZ goes down, let's say mid-transaction? Great question. Let me actually go to one of my slides that can help um, with that. So over here, let's say, so CockroachDB, what it does is it implements consensus-based transactions. So let's say your transaction was ongoing and or a region or easy went down in this region, in this case, right? So if the data that you were interacting with wasn't like a leader as part of your consensus group, your transaction just goes through as it is because you still have a consensus along with the leader that still survived. But let's say if a leader went down as part of that, what happens is you implement some retry log. We expect some retry logic to be there within that transaction loop that you have. And in that meantime, while it goes through that retry logic, the leader election happens. If a leader was down, a new leader is elected. But in this case, you still have consensus. You have a majority available. So they form that consensus group and then they process the transaction as it's occurring. So it just essentially, from the application perspective, it just does a application like client side retry from your side, and it goes through once that new leader is elected without it erroring out in other cases. I hope that answers the question. All right. All right. I see a lot of these questions already been answered in the Q&A. I'm gonna go ahead. There's not any other questions. So let me go ahead and stop sharing. There's another one. So how does the index avoid hotspots, especially under high volume or queries? So essentially, with CockroachDB, the way that we store data, and like everything's the underlying storage layer is a key space that's kind of divided into chunks, and it's sorted lexicographically. It's sort of based on the primary key, and Jim can, we have someone in the background can keep me honest here. But the way that we avoid it is make sure that the primary key that you use is non-sequential, and if it just happens to be a sequential primary key that you can avoid, you can do a hash sharded index. But that's essentially making sure that those um, the index stays randomized enough to avoid contention, um, to you know to avoid hotspots at that point under high volumes or high queries that like high number of queries that are coming through.
And was that question, I don't know if that question was specific to like vector indexing, but in general, we have this
Yeah,
background process where we're breaking data down into what we call ranges, and
yeah,
each one of those ranges is a maximum size of 500 meg. So
yeah,
if a certain chunk of data is beyond that 500 meg size, we're going to automatically break that down into smaller ranges and then to redistribute those across the cluster. So it is possible, in
yeah,
some cases, to get the hotspots within one range, even though it's a fairly small size. And then in that case, yeah, what the hash
yeah,
rate indexes can help. But yeah,
yeah, exactly. And what I'll do is I'm going to share this slide again. So if you open this link and actually, you can download the definitive guide as well as we have some things on Cockroach University as well that really dive deeper into the architecture and show how we architect it and design it to survive those sort of issues. All right. I think we don't have any more questions so far. Well, first of all, I hope everyone had, was able to take something away from today's session. And, feel free to connect with us as well if you have something specific that you would love to get answered. And we're more than, happy to, chat with you. So, having said that, I'll stop sharing my screen.
Thank
Right.
you, Harsh. This was fantastic. Thank you so much.
Yeah.
Thank you for having me.
Yeah. Yeah. Thank you. Thank you, Art, and thank you everyone for joining us today.